Okay, so I'm going to solve for you 3 more problems out of this chapter 6, that is problem 34, 35, and 36. So the main problem, 34, it says compute the allowable axial load on a steel channel C5 by 9 made of ASTM A36 structural steel. The channel is 112-inch long and can be considered to be pinned at its end. Use a design factor of 3. Repeat the problem when the ends are fixed rather than pinned. And then problem 34, repeat problem 34, except that the load is applied along the outside of the web of the channel instead of being axial. Axial load is when the line of action of the force of the forces of the supports of the ends are along the centroidal axis of the cross section. Okay, so let's look at the back of the book where C-channel geometries are presented. So this is aluminum. This is the steel channel. And ours is C9, C5 times 9, and so let me copy this figure quickly, because for the 3 problems, the last one, we need more geometric information from this. And then we need to, we'll discuss this, but we need to decide which way the channel is pinned. So this is a C channel, and this is the x-axis, axis of symmetry, and this is the y-axis, and this is the centroid. Okay, the table is going to, so at some point we're going to make use of this value. It's called x. That's for problem the last of the 3. In addition, we need the area, and then we need the area moment of inertia about both the x-axis and the y-axis. Also need this value. Okay, and this is the width. Does it have a notation? Width. Okay, let's call this W. Okay, the problems are again 34, 35, and 36. So problems 6, 34, 35, and 36. Okay, so from the table on page 813, area is 2.64 inches squared. Area moment of inertia about the x-axis. This will be for the channel buckling in the YZ plane, Z being the longitudinal axis. So when buckling in the YZ plane, the IX is used, and this is 8.90 inches at the power 4. And when it buckles in the XZ plane, we use IY. So IY is a much smaller value, it's 0.632 inches. 632 inches at power 4. Okay. I said in addition we're going to need X value, and that's 478 inches. We're going to use W, the width. The depth is 5 inches, as in, so this is C5 times 9, so 5 inches, like the first digit. 9 would be the weight per foot, if I'm not mistaken. Okay, so W value is 1.885, 1.885 inches. Okay. We're going to calculate rate of gyration, Rx and Ry. And definition of radius of gyration, square root of I about the respective axis, I over area square root. That's Rx according to the book. So radius of gyration, square root of I over A. So this is going to be Ix over A. This is going to be Iy over A. And what do we have? So actually I have these calculated. So I have the two values. I have the A. So Rx is 1.8360 inches. The other one is only 0.4893 inches. Okay. In addition, well, we need materials properties. So we have Young's modulus, and also, so we need to extract them. Structural steel, page 793. So page, we have SY, it's 36 KSI, like in the name of the steel, A36, 1000 PSI, okay. And then Young's modulus, that is modulus of elasticity, it's a footnote here. It's 29, so E is 29 times 10 to power 6 PSI. All right, so we have everything that we need, and we calculate the radius of gyration. And so this is for later or reference. We're going to assume the book is not explicit. So you could, again, imagine the channel. So you could drill a hole or holes, centroidal holes, or through the centroid, the axis. So you can drill a hole this way. We can drill a hole, two places, but a continuous hole. Or you can drill a hole this way to produce that pin end. Again, my choice, I'm going to assume that the hole is drilled on both ends this way. Moreover, I'm going to assume that there is a means of delivering the force along the centroidal axis to be consistent with problem 34 statement. Okay. The other possibility, yes, is to drill the holes, and they might be more, or it's more convenient to drill a hole that way, because it can be directed exactly through the centroid. But let's solve the problem with the hole this way. That is drilled in the middle of the flange. These are webs. This is the flange. And we're going to analyze it in in 2 planes. So analyze for buckling in 2 planes. So again, the hole and the hole dashed, centroidal force. And remember, this was the y-axis and this is the x-axis. I have x and y, and z is going to be down, z. Okay, x, y, and z axis. I want to make sure that this is a right hand reference frame. This is the load P. Okay, so and the pin again is going along the x-axis or parallel to the x-axis. So there are 2 ways in which this column could buckle. It could buckle in the y plane, so y plane, y, that is yz plane, yz plane buckling, or it could buckle in the xz plane. Okay. So in the YZ plane, we're going to use the Rx value, and the XZ plane are the RY value, which we have them. So 1.836 inches. The other one is 0.4893 inches. We calculated them earlier, and so again, YZ, this would be this type of buckling. Okay, coefficient, and we call it Kx. This is end fixity, like pin, and both theoretical. We're going to use practical values. Is going to be 1. So in the XZ plane, because I have the pin that I cannot twist, the buckling will happen like so, with the preservation of the or no change of slope. That is, the slope is 0. Here slope changes. So Ky, we call it, and this is going to be the practical value. The theoretical value is 0.5. Practical value is 0.65. So let's use 0.65. Okay. We can now calculate the equivalent stress. We have L and L is 112 inches, so equivalent length and equivalent length. So what are the value here is 1 unchanged inches, and 0.65, so Ky times L is 72.8 inches. All right. So K x times L. Okay. In addition, we need to calculate. So bookmarking this. So let's go to where the first flowchart is. So we calculate the equivalent length. We have calculated radius of gyration. We calculate the slenderness ratios, SRX and SRY. Slenderness ratio is equivalent length over R about that respective axis. So equivalent length, and in the Y now over RY. Alright, so we have the flowchart says divide equivalent length K times L by the minimum radius. There's a difference, of course, between the n fixities, so I'm not taking the minimum of the two, rather I'm taking the one that's associated with the buckling in the respective plane. So buckling in the xy plane, I'm using the Rx value. Hope it's clear. So 112 over 1.836. This is 61.002. This other one, it's 72.8 over 0.4893. 4893 equals. This is 148.8. Alright, so we have the slenderness ratios. We extracted, following the flow charts, we extracted the properties of the material. We need to calculate now, and it's the same for both planes, the Coulomb constant. Coulomb constant is 2 pi squared E over Sy at 1 over 2. This is the square root. So we have 2 times pi squared times 29 exponent 6 over 36 exponent 3. Take the square root. So it's 126.099, 126.1. Okay, so we have one value that is sorry for the background noise. So one value that is a slenderness ratio is less than the Coulomb constant. So here we have buckling, plastic buckling according to Johnson. So we calculate the critical P critical, and this is for about x-axis, the YZ plane, and it's area times yield strength over 1 minus yield strength times K times L over R. That's the slenderness ratio, SRX, and it's squared over 4 pi squared times E. The other one is, we have Coulomb constant and slenderness ratio. The slenderness ratio is bigger than the Coulomb constant, so we have Euler case. So critical load about the y-axis, it's pi EI over equivalent length squared. So let's calculate these two values. And I forgot a square here. So pi squared EI over LE squared. And all right. So let's do this. Let's do this one. The Johnson's case. So what do we have? We have 36 exponent 3 times 61.002, and this gets squared over 4 over pi squared over 29 exponent 6 equals, put a minus, plus 1 equals, times the area. Area is 2.64 times yield strength is 36 exponent 3 equals. So I have 83,919.1 pounds. The admissible load is going to be a fraction of this, that is dividing by the design factor. We have design factor N equals 3. So if we take a third of the calculated critical load, we have 27,973 pounds. All right. And then for this other case, we have pi squared times 29 exponent 6 times I, and of course is going to be IY, which is times 0.632 equals over equivalent length 72.8 squared equals, it's 34,131.3 pounds. If I divide this by 3, I get the equivalent, the admissible load. It's 11,377 pounds, which is less. So the way the column would buckle is because of elastic instability and it's going to buckle in the XZ plane, that is this way, all right, and not the plane sort of perpendicular to the paper, or looking at this. And again, the way I represent, so buckling will happen this way. All right, so we solved problem 34. Problem 35 now, it says consider the ends fixed rather than pinned. Well, it means that the same end fixity will happen about the x-axis or in the y z plane. So we have this value changes. Kx is now 0.65. Again, this is for problem 635. And how is this going to propagate? So I have the equivalent length changing. I actually have it calculated. So LEX is going to be 72. inches. The result on the right column is the same for problem 34 and 35. Column constant unchanged. So I need to recalculate the slenderness ratio. So I have 72.8 divided by the Rx value 1.836836 equals. So this goes to slenderness ratio is going to be 39.65, and then this propagates here, and there will be a new value. So we have slenderness ratio, we square it, times 36 exponent 3 over 4 over pi over 29 exponent 6 equals, put a minus info on, plus 1 equals, times area, so times 2.64 times 36 exponent 3 equals. So I have 90,341.4 pounds divided by 3. This is, so P admissible 30,113.8 pounds. Again, this stays the same. The answer is same as for the previous problem. The smallest value is this one. Okay. So this is the answer. And this is the answer. I can use the blue answer. All right. I actually solved the problem for the other, drilling the hole the other way. And if my calculations are correct, which I believe they are, the admissible load is less than 5,000 pounds. So it's a better approach to drill the hole as shown if there is a need to pin the ends. So this is a better approach. Or drilling the hole here is a better approach than this one, provided that you can, again, deliver the load axially and not in the whole area. Problem 36, it's actually considering that case, and we have, it says repeat problem 34, except consider the load to be applied along the outside of the web of the channel. So we have the same pin, but the force now goes here. Okay, so this would be the case of a eccentric loading. I'm representing the channel only okay, just the portions of it. So the force now, again, it's pinned, and the force is at the edge of the outside of the web. So as it's buckling, remember we have the centroidal reference frame. So how is this going to buckle? Is it going to bend this way, or is it going to bend this way? The answer is the column or the channel will buckle this way. So let's first look back. So okay, so I took the case where the hole is the same as but the force is now applied to the web. It's likely, looking at the two values, likely that buckling is going to occur in the x, the z plane, y, and this is the z axis. All right, and the n fixity is going to be k y 0.65. Okay, buckling is going to occur like so, again in the xz plane, and we have a case of eccentric loading. So eccentric loading, paragraph 612. We can only state the equation. To solve it, you need to do it numerically. That is, to iterate, or you put the equation in Excel and you manipulate PA until the yield strength, required yield strength, is the given yield strength, 36 KSI. So I have IY, this is equation 615, design factor times admissible load, which I want to find, over area, and 1 plus E times C over R squared secant, instead of KL, I'll put S, slenderness ratio, over 2R, and then there's N times admissible load, so N design factor over A over E, close parenthesis, close bracket. Okay, so let me use red color to populate this equation. So I have 3, this is the unknown and occurs, so there's no way you can solve this closed form, you need to iterate. What is E now? So E is the eccentricity from the neutral axis to where the load is applied. If we look at this, so E is going to be our X value, what we extracted from the appendix, from the back of the book. So E is 0.478. C now, if you look here, C is distance from the neutral axis to outside of the section. Again, we agreed that buckling happens this way, so we have the C value is going to be this piece. So C value is going to be W minus X, and that's 1.885 inches minus 0.478 inches equals, and it's 1.407 inches. Okay, so 1.407. R, it's going to be Ry, because buckling happens in the XZ plane. Slenderness ratio is going to be the Y version, R again here. Alright, so let's further explicit the equation. So Ry was 0.4893. Slenderness ratio, that's calculated. It's so again in we have the like a fixed ends. It's not going to make use of the rotation allowed by the pin. The 2 pin ends. All right, so slenderness ratio is going to be the KY times L, that's 72.8 inches, divided by Ry, that's, so the answer is 148.8. Okay, 148.8. Okay, this is 3 again. This is the unknown. Area, we have it 2.64, and this is again, of course, 29 times 10 to the power 6. Okay. And this value is 36,000 psi. So really what you need to do, put this in Excel. Excel has a solver built in. If you know how to use it, use it. If not, you can just manipulate PA until this equation gets very close to 36,000. Okay. So this being said, I'm going to pause. Okay, so I'm continuing recording. I use Excel to iterate, so I had this equation put in Excel, and I manipulated PA until I got this very close to SY. The answer is 920.474. Very sensitive to, you know, slight change of by just 1 pound throws this value to quite large amounts. What we can do, of course, is to verify if, and it should, I mean, I use Excel, and so again we have this 920.474, and this one here 920.474 pounds. Okay, by making it 920.475, it goes slightly over 36 psi. In any case, if you compare the values, there is a substantial reduction in load carrying, like more than 10 times reduction in load carrying capacity if we have the load applied not centroidally, but like how much? Less than ½ an inch off the neutral axis, centroidal axis of cross section. Okay, so we can evaluate this, apply secant 1 over cosine. So we have 3 times 920.474, and I'm going to put this into memory, over 2.64 over 29 exponent 6 equals, take the square root, times 148.8 over 2 over 0.4893 equals, so I have this whole thing, cosine, and then take the inverse. Alright, so this has been taken care of, times 0.478 times 1.407 over 0.4893 squared equals, plus 1 equals, times 3 over 2.64, the area, times, have it in the memory, equals, and whatever. Okay, so I need to confess, Excel uses more decimals for some of these terms. So the answer is no answer. Probably I missed something, some calculations. Anyway, it's 10 p.m. time I'm recording. Feel free to implement this in Excel. Have a cell that is labeled PA, and you manipulate it, or rather try my value and see if implemented in equation 615 it gets you SY, the required yield strength, very close to, or close to 36,000 PSI. Okay, so recording stops here. Thank you for watching.